This video shows the components of the Dismount Alert device, as well as the video demonstrations of the working components. Pictured here is the CAD model of our device. The device features two physical components, the speed bump and the truncated domes. The truncated domes are placed 10 feet away from the speed bump. Here is a photo of the Dismount Alert device high-fidelity working prototype. The speed bump is on the top end of the photo, and the truncated domes are on the bottom end of the photo. An Arduino Uno is on the left-hand side of the photo. The Arduino Uno is used to control the electrical system of the Dismount Alert device. Force sensors are placed underneath the truncated domes. Data from the force sensors is sent to the Arduino, which is then able to control the device's lighting system. In this photo, a force is applied to the truncated dome force sensor system, which causes the device's lighting system to turn on. Note that the truncated domes are placed closer to the speed bump for demonstration purposes. This photo shows the device's wooden frame and supports. The frame is held by triangular supports that connect to the frame in rectangular patterns. The wooden frame and support system has been tested to hold at least 500 pounds. This video demonstration shows the effect of a horse stall mat on the wooden frame. A horse stall mat is added to provide extra traction. In this demonstration, a wheelchair wheel is being rotated along the horse stall mat. The horse stall mat has been tested against the bare wooden frame to provide more traction. This video shows a side view of the device's lighting system. The lighting system is composed of a weatherproof LED strip. The lighting system is able to be controlled with the electrical system's Arduino. This photo shows the device's photoresistor array. The photoresistors are a part of the electrical system and send data to the Arduino. The Arduino processes this signal and then turns on the device's lighting system when the ambient light drops below a certain threshold. This photo shows the device's lighting system turned on in a dark room. As mentioned in the previous photo, the Arduino turns on the lighting system when the ambient light drops below a certain threshold. This system was tested in a variety of light conditions and was able to successfully turn on when the ambient light dropped below the light threshold. This photo shows the device's force sensor array. The force sensors are placed beneath the truncated domes. The force sensors are the long black strips that run along the underside of the truncated domes. Three force sensors are used to determine whether or not a force is being applied to the truncated dome force sensor system. When a force is applied to the system, the force sensors send a signal to the Arduino, prompting the Arduino to turn on the lighting system. The device has been tested in various conditions and responds to most forces applied to the device. This video demonstration shows the effect of a force being applied to the force sensor pressure plate. This setup shows three truncated dome tiles with a force sensor pressure plate underneath. A force is applied to the force sensor pressure plate. The pressure plate then sends a signal to the Arduino. The Arduino is then able to process this signal and then sends another signal to the LED strip to turn on. The lights turn on in response to a force being applied to the sensor. This video demonstration shows a person on a bicycle riding over the truncated dome force sensor system. When the person rides over the system, the device's lighting system turns on. The LED lights are also lit at a lower brightness before, after, and in between the cyclist going over the truncated dome force sensor system due to the ambient light conditions. Note that the truncated domes are placed closer to the speed bump for demonstration purposes. Similarly, note that the LED lights appear to be pulsating on the video due to the video camera's settings and not due to the lighting system.